Okay, so moving on to 2014, consider reversible equilibrium reaction. So we got nitrogen monoxide produces nitrogen gas and oxygen gas, and we've got a delta H. It says the equilibrium constant of 20.25. So again, Kc is 20.25. So because we've been given Kc, it's more than likely we're going to end up with algebra somewhere here. It asks you to write the equilibrium constant expression for the reaction. So let's start with that. So Kc. Kc is going to be equal to the right hand side, which is N2 concentration, and O2 concentration all over NO. And because there is a 2 in front of the NO in the equation, that makes it squared here for Kc. Calculate the number of moles of nitrogen gas in the reaction mixture at equilibrium when a 2 mole sample of nitrogen monoxide decomposes to nitrogen gas and oxygen gas. So let's just go back and grab the table. Okay, so we're back here now at the table and we can start filling it in. This particular question is actually one of the best questions to show the confusion that can often creep up with students. So let's fill it in and we'll see where the confusion lies. So we've got 2NO, and that's the start, and then our equilibrium symbol, we got N2 and we've got O2 here, and we've got to fill in our initially. So according to the question here, what have we got? We have a 2 mole sample of nitrogen monoxide decomposes. So we're starting with 2 moles initially. So we can put in 2 there. Just fix that. So we've got 2 moles here. And again, initially we have 0 here and 0 here. We've nothing at the start. So what's the change, or have we got something at equilibrium that could give us an idea? We have no other information about what occurs at equilibrium, and we've no information about the change. If that's the case, then what you have to do is try and consider what the change is going to be. So obviously we don't know how much is going to be used up, so we put in X. Because this is a 1:1 ratio, we put in X here as well. When we come back over this side, we have to try and figure out what to put in here. Normally what would happen here is we would put in, because these are positive x's, normally what would happen here is we would put in negative x. But we can't do that here. We're not going to do this. The reason why is because this is a 2 here. So this is a 2:1. So whatever we have here, because it's a 2:1 ratio, this one here has got to be doubled on the left hand side. So this one here has got to be 2x. The reason why this here is 2x is because of the 2:1 ratio up at the top. The reason where the confusion starts here for students is because they often look at this x here and this x, and they think that x plus x equals 2x. And that's not where the 2x is coming from. The 2x is coming from the ratio. It's nothing to do with these x's being added together. So students will often say sometimes, you know, why do you add them together? Sometimes you don't add them together. You never add them together. The number that you have here is always dependent on the ratio of the reactions with the molecules. So hopefully that kind of clears that up, and that's always where students have that issue. Okay, let's get rid of that. And then you can just fill in the rest of the details. So over here, if this is a change, so this has obviously got to be negative 2x. So at equilibrium, it's 2 minus 2x. Here, this is positive x, and this is positive x. There is nothing in the container about volume or anything like that, so we assume that it's a 1 litre container. So once that's in, then you're obviously going to start doing the maths. So pop in the numbers. So the first number you're going to put in, well, N2 is x, O2 is x, and the NO is 2 minus 2x, and that has to be squared. Now in this question, it tells us that Kc has a value of 20.25. So all of that is equal to 20.25. So you work down through the question. So what have we got? X squared on the top, and we've got 2 minus 2x to be squared on the bottom, and that equals 20.25. At this point now, you can get the square root of both sides. So if you apply a square root to this side, it gets rid of the squares, but you're going to have to do it to that side as well in order to keep it balanced. So that leaves us with x over 2 minus 2x, and that equals the square root of 20.25, which I worked out to be 4.5. And now from here, you're just going to do some basic algebra. So your algebra here, you're going to bring this particular part across and multiply it in. So we have x is equal to 4.5 multiplied by 2 minus 2x. So x equals 9 minus 9x. And then you bring your x's to one side. So we've got x plus 9x equals 9. So we have 10x is equal to 9. So x is equal to 0.9. And that there is your final answer. X is equal to 0.9 moles. So that's 2014. Let's move on to 2013. Okay, so continuing on with 2013. Question looks initially a bit difficult, but it's actually not too bad. We've got iron 3 plus ions and they're reacting with CNS. So your CNS is the part of a thiocyanate. In this case, it's potassium thiocyanate, and that's reacting to give this iron thiocyanate. Let's work down through the questions. I'll grab a table and I'll come back. So here's our table. Let's continue on. So what have we got? We've got Fe3 plus. We have our CNS negative and our equilibrium sign, and then we have our FeCNS 2 positive. So again, initially, let's look at the question. So it tells us that in the question, we have a mixture of 1.0 by 10 to the minus 3 moles of each of iron 3 chloride and potassium thiocyanate. So that's our first one. So initially, we've got 1.0 by 10 to the negative 3, and we've also got the same here, 1.0 by 10 to the negative 3. Of course, we have 0 here because nothing at the start. Then, as the question goes further down, we can see 1.1 by 10 to the minus 4 were present at equilibrium. So what have we got? At equilibrium, we have 1.1 by 10 to the minus 4. From this then, we can work out all the other parts. So obviously, this is a plus 1.1 by 10 to the minus 4 to get to that. And because this is a 1 is to 1 is to 1 ratio, that means this is 1.1. This is 1.1 by 10 to the minus 14 as well. Or sorry, minus 4. This is also 1.1 by 10 to the minus 4. The difference with the left-hand side is on the right-hand side it's positive, so these have to be negative. So up here you're going to do 1.0 by 10 to the minus 3 minus 1.1 by 10 to the minus 4. And when you do that on your calculator, you end up with 0.00089. And you also end up the same thing here, 0.00089. And for continuity's sake, you can write that as scientific notation, which is 8.9 by 10 to the minus 4. And that's 8.9. It doesn't matter whether you leave it as that or not. It makes no difference. The answer is going to be the same at the end. And then what you've got to do is work out Kc. So Kc for this reaction is going to be the concentration of the FeCNS 2 plus ions. Again, this may have caused students confusion. There's no power here, and just because there's ions in it makes no difference. The notation is still the same. And then we've got Fe3 plus ions here. Again, we have no value in front of these. So because there's no value in front of these, we don't have any powers. And we've got a CNS negative there. And then just fill in all your numbers. So Kc for this reaction is going to be 1.1 by 10 to the minus 4. And all of that is going to be over Fe3 plus, which is 8.9 by 10 to the minus 4 multiplied by 8.9 by 10 to the minus 4. And when you pop that into the calculator, you're going to get a Kc value. I worked it out as 138.87, which I think is right according to the marking scheme. So that's Kc for that. Okay, moving on to 2012. Okay, so continuing on with 2012, here's the table. Let's fill in our details. We have our equation here. So we can put in our I2 here, we can put in our I minus here, and then our equilibrium at I3 negative. From this question, we can see that 0.8 moles of iodine and 0.24 moles of iodide, which is the I minus, and iodine is I2, were added to deionized water. So we can pop those in. So initially we have 0.08, and we've got 0.24, and of course we've got 0 there. The next bit then says 0.0793 were present at equilibrium of the triiodide ions. So this one here is going to be 0.0793. So the change then is easy enough. That's plus 0.0793. And because this is a 1:1:1 ratio, that means over here this is going to be minus 0.0793 moles. This is going to be minus 0.0793 moles. And then you do the calculations. This particular one leaves us with 0.0007. This one here is going to leave us with 0.1607. And then we're going to go work out Kc. So Kc for this reaction is going to be your I3 minus ions, the concentration of them, all over the concentration of the I2 multiplied by the concentration of the I minus. And pour in your numbers, stick them into the calculator and see what it works out to be. In this particular example, all that is going to be over 0.0007 multiplied by 0.1607. So Kc then is going to work out to 704.95. And that ends 2012. So that's it for the end of that video. That's probably it for the moment. I can do some more stuff. Just let me know in the comments on Google Classroom. And I can do up another video for you as soon as I get some ideas. Okay, thanks folks. Let me know if there's anything I can help you with.